All right, guys. So we are going to go today and start the last topic in this unit, okay? And that is projectile motion. I'll kind of introduce it today and maybe try and give you a little bit of time at the end of class to work on your vector assignment a little bit more. But this is what we'll be doing for the next few days because there's quite a bit to it, all right? The reason we do projectile motion last in this unit is because it uses everything from this unit except gravity. Right? So you're going to have to use v equals d over t. You're going to have to be able to find vector components. You're going to have to use acceleration formulas. All of that stuff is part of projectile motion. Okay? So we'll start off with what is the definition of a projectile. So a projectile is any object that is in unpowered flight in the Earth's, we'll say atmosphere, but truly it would be gravitational field. Okay? And we say gravitational field because satellites, which are not in the Earth's atmosphere, but are in the Earth's gravitational field, are technically projectiles. And what we'll learn in our last unit is that the way to make something orbit the Earth is to make it go fast enough that it does the same thing something on Earth does, which is like when you throw something, it arcs back to the ground. To make something orbit the Earth, you just make it go fast enough so that that arc never encounters the Earth, and instead becomes a full circle. And then it will orbit the Earth. Okay? The earliest ideas of this were by Newton. Okay? Now, Newton's like the most important guy in terms of like classical mechanical physics. It got to the point where he was doing stuff that was so far outside of what anyone else was thinking about that there wasn't the ability to run actual experiments and test it. So Newton would run thought experiments, which would mean he'd think stuff up and then put it on paper and go, see how smart I am? Okay? And one of those things was how to make something orbit the Earth. Okay? And that was that it had to be a projectile, but it just had to go really, really fast so that it didn't curve back and hit the Earth. It just orbited. Now, his idea was put a cannon on top of a really tall mountain and fire it, and that cannonball would go all the way around the Earth and come back. Now, in order to make that happen, it would have to move at like 8 kilometers per second, which would incinerate the cannonball. Okay, that's why things burn up in the Earth's atmosphere. They're going really fast, and there's lots of air resistance, and they burn up. Okay, but the idea was sound. Okay, a projectile is something that is in unpowered flight. It doesn't have a motor, so a plane is not a projectile. A rocket is not a projectile. Okay, it has to be an unpowered flight in the Earth's gravitational field. Okay, now that motion has 2 dimensions because anything that's caught in Earth's gravitational field is going to move vertically downward. Why? Because of gravity. Yeah, gravity pulls towards the center of the Earth, which no matter where you are, because the Earth is round. By the way, if you like are part of the whole flat Earth idea, you should probably drop my class right now because you will hate everything from this point onward that I say, because I'm right. And flat Earth is silliness. Okay. Anyway, that aside. Okay. The Earth is round. Oh, right, we covered that. It's round. Okay. And any point on the Earth, gravity pulls towards the center. That means down. Okay. So even though the Earth is round, okay, always it's pulling towards the center, which for us we sense as downwards. So any projectile flying through the air is going to be pulled towards the Earth. Okay, towards the Earth's center, in fact. Okay. The other dimension to the motion is horizontal. Okay. When you throw something, it does move horizontally, but then arcs down to the ground. Everything arcs down to the ground. Okay? It is impossible to throw something perfectly horizontal, okay? Because gravity will always pull it downwards. Okay? Now, as a kid, you probably experienced this, or maybe even last summer you experienced this. Okay? If you've ever like played with a hose, okay, like you wanted to get somebody with the hose, but they were just a little too far away because the water arced down and you couldn't get them. To make the water travel further, all you had to do was okay, you can put your thumb on it and increase the pressure. Let's say you're using a nozzle and it's already all the pressure you can get. Just aim up. Yeah, because what you do by aiming upwards is instead of having it arc like this downwards, you make it arc like this, and it travels farther. Okay? It's like if you're throwing a Hail Mary pass in a football game, you don't try and throw it horizontally on a rope. It's only going to travel 15 or 20 yards before it hits the ground. Okay? If you want to throw that big, deep bomb, you aim way upwards and you throw it way up in the air so that it has a longer hang time, okay, and will travel further horizontally before gravity inevitably pulls it back down. All right? Everybody okay with that? Okay. So the essence, essentially, of all projectile motion is this two-dimensional movement. Okay? How many people have ever done like any target shooting, like with a bow and arrow or a rifle? Okay, so the further away the target gets, obviously the harder it gets to hit. Because now you have to correct for what?
Wind, gravity.
Wind and drop are the two biggest ones. We talked about this when we talked about that rifle question back in the acceleration lesson. Okay? We have to correct for the fact that a bullet is going to drop. Okay? The day we talked about that question, we figured out that over a distance of like 3.5 kilometers, the thing was going to drop like 70 some meters, okay, from its original height. So if I'm trying to hit a target, okay, so here, and I'm standing here, I don't aim for the target, because if I do, that's what's going to happen. If I want to hit that target, I have to aim above it and let gravity bring it back down to the target. Okay, everyone kind of makes sense? Okay. Now, here's a question for you. I have 2 bullets. One of them is in a rifle, and the other I'm just holding. Okay? With no one obviously in front of me. Okay? I pull the trigger on the rifle, and I drop the bullet at exactly the same time. Which one hits the ground first?
Gravity.
They hit at the same time. They're going to hit the ground at the same time. Not in the same place. Okay, I will grant you that. They're definitely not going to hit the ground in the same place. The one that drops is going to hit the ground right in front of me. Okay? The bullet that's fired is going to hit the ground way out there. But they're going to hit the ground at the same time. Okay? Here's why. They are both going to fall the same vertical distance at the same rate of acceleration, and they both have the same vertical initial velocity. What is their initial vertical velocity? 0. Okay? Even the bullet fired from the gun is not moving vertically when I pull the trigger. I've aimed the gun horizontally. Okay? So yes, it's going to travel horizontally a long way, but it still does all the same vertical stuff. Okay? So if I was actually watching just the vertical part of both of those bullets, okay, motions, I would see exactly the same thing. I'd see an object falling to the ground. Okay? If I turn to the side and watch it, then I see something completely different. I see one bullet falling to the ground, and I see one bullet traveling horizontally and arcing to the ground. Okay? But the vertical part for both of them is exactly the same. Okay? Everybody all right with that idea? Okay. So that means then that the simplest projectile is a falling object. Okay? That is an object that is in unpowered flight in the Earth's atmosphere. Think back to Toy Story. Okay? When Buzz, did this whole thing, right? He was like, I'm flying. No, that's falling with style. Right? And if you're falling, you're still flying, just with style. Okay? All right. So let me give you another hypothetical situation here. Back in the late 90s, Lexus had built this sports sedan, so 4-door sports car. And they came up with this awesome advertising campaign because they were trying to kind of cut into the market for BMW. You all right, Ty?
Yeah. Can I go to that?
Yes, absolutely, please do. So they were trying to cut into the market of all the European automakers, BMW, Mercedes, okay, things like that. And so they built this really, really fast 300 horsepower sports sedan. And their advertising campaign was this: the Lexus IS300 is faster than gravity. And they made an incredible ad to show it. Now, it was trickery, but it was a good ad, and it worked. I'm going to show you that. And I want you to see if you can figure out what's wrong with it. balance. Okay, so I've got gravity pulling down, I've got air resistance pushing up, and this thing reaches its terminal velocity and doesn't accelerate anymore. Well, I can make a car on the ground go way faster than the terminal velocity of a falling object. Did you also notice that that car fell like this? Should a car fall like that? No. A car should nose down like this and fall in its most aerodynamic dimension. It would definitely win if it did that. They weighted the car. Okay? They put a whole bunch of weight in the trunk so that it would fall like this, okay, in its least aerodynamic dimension and have the lowest possible terminal velocity for a falling object. Meanwhile, a car on the ground is under power, okay? It's continuing to push and traveling in its most aerodynamic dimension. It's definitely going to win, okay? And it should win every single time. But it's not outright shown that that's what's happening. So it's not really false advertising. They did show that the car on the ground started first, okay? But then they talk about they're going to travel the same distance and everybody gets totally impressed again. Okay? Advertisers are clever. Okay? They want to trick you. Okay? And that ad tricked a lot of people. It was impressive when you watched it, wasn't it? This falling car on the ground, there was tension, and the car on the ground got there first. It was exciting. Okay? But it was also full of crap. Okay? You can make anything look cool if you set it up right. Okay? And this is just simple projectile motion. Okay? That projectile could only go so fast. All right, so if we're looking at just a falling object, it obviously only has one dimension to its motion. Okay? If something drives off a cliff, then it has two dimensions. Then it is moving horizontally as well as vertically. Okay? Now, which one becomes the dominant one pretty quickly? The vertical one. Okay? But if you've ever watched, a movie where something drives off of a cliff, okay? So here's your cliff. It starts out like that, but then it's very quickly becomes like this. Okay? Reason being, once the car drives off the cliff, it can no longer provide forward propulsion. Okay? It's not like Wile E. Coyote, okay, where it'll just hang there until it realizes it's not on the ground anymore. Okay? It's just no longer pushing. Okay? So it'll eventually go down to the ground. Okay. So I'm going to show you the Mythbusters actually busted that. Right? Like the car in the ad drove across the X, and then the other car slammed right down, like within less than a second behind it. Okay? Here, the car that was falling hit the ground quite a bit before. Okay? The car falling hit the ground before the car on the ground got there. And it's just a matter of there were probably a few variables that were a little bit different. Okay? Elevation, distance from the equator. Okay? Who knows where they filmed the other shot? See, so lots of things can affect that because depending on where you are on Earth, because the Earth's round, gravity changes. Okay? Gravity isn't equal at all places on Earth because Earth's not perfectly round. It's not flat, but it's not perfectly round. Okay? It's actually somewhere between a football and a basketball. Okay? It's not a football, it's not squished that much. Okay? But it's not a perfect sphere like a basketball either. It's squished a little bit. Okay? And so as a result, where we are, we actually experience a greater acceleration due to gravity than you would if you were at the equator. Because at the equator, the Earth's wider. And if you're standing on the surface at the equator, you're further from the center. And you'll weigh less. Okay? Here you would weigh more. So you just want to lose a pound, just go to the equator. You'll weigh less. Okay. All right, is everybody kind of following what we're looking at there? Okay, so as we said, okay, anything that goes up has to come down. That's how a projectile works. Okay? If I throw something up in the air, it comes right back. Now, if I throw something up in the air, okay, so I throw it from this height, just have my arm level, right? As I throw it up, okay, it comes back down to my hand. Now, how do the speeds that it leaves my hand and returns to my hand compare? They're the same. Okay? Why?
The amount that the force you gave it will reciprocate when it's coming back down?
It's possible that could happen, but it doesn't have to be true.
Is it because how however you throw it, it'll go to a certain speed or certain height, and from that height it'll drop, and the more height it has, the faster it'll go down. But
Yes, yeah, that's certainly part of it.
yeah,
Okay, so think about this. I threw it and caught it in the same position. That means it traveled upwards and downwards the same distance. Agreed?
Yeah.
Okay, and once it left my hand, what was its rate of acceleration once it left my hand and I wasn't throwing it anymore? What was the only force acting on it once it left my hand? Gravity. Right? So it accelerates, once it leaves my hand, it's accelerating downward at 9.81 meters per second squared. That's why it's going slower and slower and slower. And when it's at its maximum height, how fast is it going?
0.
0. And then it goes from 0 and falls exactly the same distance at exactly the same rate of acceleration back to my hand. It's like looking in a mirror for motion. Those two motions are the mirror images of each other. So if it left my hand at positive 3 meters per second, it's returning to my hand at negative 3 meters per second, because A and D are equal for both parts of the trip. Okay, that sort of makes sense. This one ends at 0. The fall starts at 0. So when it comes back down to my hand, it has to be going the same speed it left at. Okay? Now, that's an important idea, especially in terms of safety. I mean, there's a lot of reasons why you're not supposed to discharge a firearm inside of city limits, okay? Obvious reasons, okay? But there's also a good physical reason. Even if I shoot a bullet straight up in the air, when it comes back down, in the perfect physical world, it would be going the same speed I shot it at. Would you agree? Yeah. Is that what happens in the real world? It's not, okay? If I shoot a gun straight up in the air, the bullet will go up, it'll stop, and then it'll start to fall back down. But when it falls back down, it tumbles. Okay? It doesn't fall point down. Okay? If it did, then it could be when it got back to the ground going the same speed, but it doesn't. It tumbles, and as a result reaches a terminal velocity and doesn't accelerate past that. Okay? So there's kind of less danger of that. But the danger is if you don't shoot it straight up, but you let it go in an arc. In the arc, it will travel in its most aerodynamic dimension, and when it returns to the ground, it will be going the same speed it left at. Okay? And that could be a lethal speed. Right? So we have to consider that. Okay? All right. Now, projectile motion, when we see it on screen a lot these days, is fake. And sometimes it can really look fake, because we have kind of an innate or evolutionary understanding of how things should move. Okay? And the era of CG has kind of ruined that. Okay? Now, if you want to make a scene of a car jumping over a bus, you just tell the CG guy to make it happen. Okay? And then you don't have to wreck a car, endanger a stuntman, okay, or any of that kind of stuff. Okay? Back in the day, before CG, you had to jump a car. There had to be a guy at the wheel, okay? And he had to land it. Right? You had to film the whole thing and not screw up, or you'd have to wreck another car. Okay? There was a lot more planning that went into projectile kind of based stunts, okay, back in the day. Now they don't have to do that. So let's have a look here. Some examples. Okay, so what we saw there is basically this. Okay, car drives off a cliff and then does this. But what we need to understand is there's two motions happening at the same time. There's a constant horizontal motion and an accelerated vertical motion. Okay, everybody kind of with me there? So it's kind of like a boat question, actually. Okay? In a boat question, you're traveling across the river and down the river at the same time. Well, in this, you're traveling horizontally at a constant velocity and accelerating downwards, which is why it looks like by the end they're only moving vertically. They're still moving horizontally, though. Okay? It's just that the vertical part becomes dominant pretty quickly, becomes a lot faster than they were moving horizontally when they drove off. Okay? The same is true if you're like at a pool and you run off the diving platform. Okay? You continue to move forwards, but gravity propels you downwards faster than that pretty quickly. Okay? Does that sort of make sense? If you've ever like run off the diving platform, okay? Especially like the 10-meter one, the really tall one. If you run off of that, you can really kind of get a sense for what that's like. So let's set this up. I want you guys to copy this down as our first example of a horizontally projected projectile. I don't draw well. That's a car. Okay? It looks like a hamburger with eyes, but it's not. Okay. All right, so the hamburger with eyes, car, is going to drive off the cliff, and we'll say it's going to drive off at 20 meters per second. Okay. The cliff is going to be 100 meters tall. How far from the base of the cliff does the car hit the ground? Okay, now here's the thing we have to remember. In all projectile motion, there are two parts to the motion, the horizontal part and the vertical part. And they only have one thing in common. Just like in a boat question, the only thing they have in common is how long they happen for. Ty, question.
Would it be the calculation of whatever gravity would be, so figure out how long it'd fall, and then just times that by the meters per second, just times, if you go 20 meters per second, it falls for 10 seconds, times 20 by 10, that's the distance.
Exactly, because the only thing they have in common is time. Once the car hits the ground, it's no longer moving vertically or horizontally. Okay, so the only thing they share is time. Everything else is different. So what we typically do with all projectile motion problems is we break them up into their vertical and horizontal parts. And we write down what we know for both of those. The question wants to know how far from the base of the cliff the car is going to hit the ground. That's how far the car travels horizontally. Okay? So I'm looking for the horizontal distance. I'm told that the car is moving horizontally at 20 meters per second. Okay, that's all I know horizontally. What do I know vertically?
The acceleration.
I know the acceleration. Okay, 9.81 meters per second squared down. In this question, that's not going to be all that important because everything is down. But once we start dealing with things that start upwards, it becomes pretty important. Okay. What else do I know vertically?
The 100 meters.
The 100-meter distance. And what else do I know vertically? I know one more thing. No, I don't know the final velocity, and we often want to say that, like, oh, final velocity is 0. Actually, that's an entirely separate acceleration, okay? It decelerating after hitting the ground is an entirely separate deal.
Initial
Okay.
velocity,
What's the initial velocity?
20 meters per second.
The 20 meters per second is horizontal, right? It's not moving vertically at 20 meters per second.
Zero?
Zero. That's the trick. That's what people forget when they're doing a horizontally projected projectile. They forget that it wasn't moving vertically at time 0. It drove horizontally off the cliff. So VI is 0 meters per second. All right. If I want to find the horizontal distance, I need the time, agreed? Because we said it's going to travel at a constant velocity horizontally. The formula for constant velocity is v equals d over t. Vertically, it's going to accelerate. Do I have enough information here to calculate how long it falls for? I do. Which formula should I use? Ty?
Equals vi times v plus 1 over 2 times acceleration times time squared.
That one, yeah. You know that one I told you you'd never have to use to calculate time? Unless
VI was 0.
VI was 0, which it is. All right, so I can manipulate this to solve for time. Okay, I'm going to divide both sides by half of a, and then I'm going to square root. See what I mean? Acceleration is going to come back into this. We're going to be using all of our acceleration formulas when we're doing projectile motion. All right, so then time is going to equal 100 meters divided by 1/2 times 9.81. Since they're both down, I'm just going to make them both positive. I could also make them both negative if I wanted to. Okay, but just for the sake of simplicity, it only moves downwards. Okay. Okay, and notice I'm enclosing the bottom in brackets, okay? Otherwise it'll do order of operations and I don't want it to go from left to right. I want it to divide the top by the bottom.
Wait, so I know you divided by 1/2 of a, but how did that get rid of VIT?
Oh, because VI was 0.
Oh, right.
Yeah. Okay, so it's going to fall for 4.515 seconds. Okay, so roughly 4.5 seconds it's going to fall for. Okay, this is the one part that both the horizontal and vertical share. Because they both happen for the same amount of time. Once it hits the ground, they both end. Okay, so now I've got that. And just as Ty pointed out earlier, now I can calculate D because I have both V and T. So I take my 20 meters per second, multiply it by 4.5, and that should be 90 meters, yeah? So it travels further vertically than it does horizontally. Okay, that vertical part became dominant pretty quickly.
Do you have to add a vector to the horizontal distance?
No, because the question asked how far from the base of the cliff. It didn't give us didn't say 20 meters east, meters per second east. Then you would have to say it lands 20 meters or 90 meters east of the cliff. But I can't remember the last time I ever asked one that way.
So if you had a 10-meter cliff and you were still going 20 meters per second, would you go further horizontally than vertically?
Yeah, definitely, because you wouldn't accelerate very much on a 10-meter cliff. Okay, is that sort of making sense? Right? Like, there's no one part of projectile motion that's terribly difficult. You guys know how to use acceleration formulas. You know how to use v equals d over t. It's a matter of putting them all together in the context of a projectile question. That's kind of where the difficulty comes in, right? So these are horizontally projected projectiles. We're also going to look at angled projectiles. Because in the end, most of the time, if we're throwing something or shooting something, it's at a slight angle above the horizontal. Okay? All right.